a new week of the Shutdown Polymer conference. So today we have the pleasure to listen to Dr. Julie Diani, who's a senior CNRS researcher at the Laboratory of Mechanics of Solids at the Polytechnic School in Paris-Saclay. And so Julie, she got her PhD from the Normale Supérieure in Cachan. Now it is ENS Paris-Saclay. And Julie previously was located at the PIM laboratory in Paris and Sam. And she joined Polytechnic in 2016, I think. So it will be about polymers, but from a mechanical point of view. So please, Julie, the floor is yours, like we say usually.
Okay,
you have approximately something like 45 or 50 minutes, and then the questions.
Yeah, thanks a lot for inviting me. So yeah, I'm going to talk about viscoelasticity and time temperature superposition properties for amorphous polymers. First, so I come from a laboratory of mechanics of solids in Palaiseau, as you said, and we have 4 groups. We're not in teams, but we have groups in terms of topics we are interested in, and I'm leading the mechanics of materials group. So there are people working on polymers, but also people working on metals. We have also a group working on behavior and durability of structures, multidisciplinary mechanics, and that's, for example, all the coupling, for example, for elastomer reinforced with magnetic particles. So the coupling between the magnetic properties and the mechanics properties, but it can be also batteries. And last, biomechanical group, which is team up with some people from INRIA, and they're working on the modeling, especially modeling of the heart. So who am I? I'm a senior researcher at CNRS in the 9th section, which is interested in mechanics of solids, material structures, biomechanics, and acoustics. So I don't know anything about chemistry, and my expertise is in experimental characterization and modeling of the mechanical behavior of polymers. So everything that is relationship between microstructure and mechanical behavior. And in the section 9, we also focus on delivering constitutive equations that are useful for the engineer. So I'm going to talk about a topic that we studied with my colleagues for approximately a decade. But my current focus is on an industrial chair between École Polytechnique, so our lab, and the CMAP, which is the Applied Mathematics Department lab, and Arkema, and we are interested in design and modeling of innovative materials. So I'm leading this chair for the École Polytechnique. Okay, so what we start looking at the linear viscoelasticity and time temperature superposition of polymers, we were interested in modeling the shape memory behavior of polymers, and more precisely of amorphous network. And well, we thought it could be this property would probably be linked between the viscoelasticity and the time temperature superposition. So we looked at that, and so we look into the characterization at small strain, infinitesimal strain. Then we look at how that it extends to finite strain. And once we've characterized that, we look at how this helps predict the shape memory property of amorphous network, and can also be useful for other applications like the rebound of polymer ball, like bouncing balls. Okay, so linear viscoelasticity. So as I said, we are interested in writing constitutive equations. And so basically, it's define the relationship between the stress and strain and other internal variables that can be, for example, plastic deformation, viscoelastic deformation, damage. Here, we're going to focus on isotropic materials. So basically, materials with the same response with no privileged direction. So the same response, whatever the direction of loading. And those materials can be completely described by two moduli. So for example, shear and bulk moduli, but it can be also Young modulus and Poisson ratio or Lamé constants. And viscoelasticity is basically a time-dependent behavior. So the stress is not only dependent on the state of strain, but it's dependent on how you reach this state of strain. And the whole history of loading is going to affect the stress at time t, okay? And in linear viscoelasticity, that means that you can define the stress-strain relationship as such with g of time, the relaxation modulus. And the goal is to define this function. So what do? Usually we apply dynamic loading, sinusoidal loading. So for example, a strain defined by an amplitude, gamma naught, and angular frequency, omega. And we're going to measure the stress. And this stress can be defined with one part that is in phase with the applied strain and one part that is anti-phase with the applied strain. So the first one is define G prime, the storage modulus, and G double prime, the loss modulus. What's interesting here already, you can see that G prime and G double prime are not independent. They're both defined by the same function, the relaxation modulus. Okay, from an experimental point of view, if you apply a sinusoidal shear, for example, if the material behaves as linear, what you get in terms of stress is a sinusoidal response, like here. And so if you plot the stress as a function of strain, you'll get a nice ellipse. G prime and G double prime are calculated using fast Fourier transform, but you can also define G prime very simply like that. It's stress when the strain is maximum over the maximum strain. And G double prime is related to the energy loss during a full cycle. So the hysteresis in this on this ellipse. When you're dealing with nonlinear response of a polymer network, what you get is you apply the sinusoidal strain and you won't get a sinusoidal response, such as here, for example, for a rubber material at large strain. If you plot stress in terms of strength, since I'm in a rubbery state here, I don't have hysteresis, but I don't have an ellipse either. Okay, so for the moment, I'm just interested in linear response. So I apply a sinusoidal strain, I get a sinusoidal strain. Okay, so that's about all the chemistry you're going to see on my presentation, I guess. So we're not chemists at all, but we like to make our own material in the lab to be able to control that and not dealing with complex industrial material. So we are making acrylate network because they're easy to make. So we mix monomers and crosslinkers, and we cure them in a UV chamber. Here you see the students putting the mix in between glass plates. So we end up with plates that with constant thickness that we can cut and then test. The polymerization and the cross-linking happen at the same time. So we don't really control what we get, but what's nice is that in terms of mechanical properties, we are capable of doing simply materials that are reproducible. Okay, so the first question I asked myself, because I was at the time at the PIM, and we had two types of machine helping characterizing the linear viscoelasticity. So the first question I was wondering is, if I apply uniaxial tension DMATs or torsion DMATs, would I get the same result? So I had access to a TA DMA Q800 and a rheometer from Anton Parr, and to apply so torsion, and so get access to G prime and G double prime. Okay, so first for the uniaxial tension test. So the idea is that we want to build the viscoelastic master curve. Obviously, it's impossible to apply such a range of frequency. So we apply frequency sweeps from 10⁻² to 10 Hertz at given temperature for the same amplitude, small amplitude, small enough so we have a linear response of the material. And so we get storage modulus as function of frequency here in log scale, and tangent delta in terms of the log of frequency. And we're going to build the master curve by applying the time temperature superposition. So choosing a reference temperature here, the higher temperature, we're going to shift the curve one by one, and that's going to give us access to the shift factor for the reference temperature. And we're going to be able to build the master curve like that. Okay, so that's classic, and that gives us access to some shift factors and the material viscoelasticity. If I look at torsion test, it's a little bit more complex. First, so we're dealing here with solid rectangular samples, and we notice that if we have different geometries, here length 46 and 5 millimeter for the width, so something that is a bit slender than another more rectangular sample, and we do a temperature sweep, we have very different response, so quite different response, even though we had a temperature sweep of 1 degree by minute, which is quite smaller as a temperature ramp. So we noticed that according to the sample and the width of the sample was 1 millimeter. So we noticed that according to the sample geometry, we get different response. And so those temperature sweep are nice to get a quick qualitative idea of the result, but will never give you some quantitative data to characterize the viscoelasticity. If we do frequency sweep at if we do measure still at different temperature, but equilibrate the temperature before do the measurements, we get the same tangent delta, but we don't get the same storage modulus. And why? Because actually to get G prime and G double prime for a rectangular sample in torsion, we use the Saint-Venant approximation. And when you do that, you make the assumption that your sample is long and there's no disturbance by the grips that constrain the lateral displacement of your sample here. And so we did finite element simulations to understand this difference. And actually, you can see that the grip prevent homogeneous deformation in the smaller sample. And so if you want to have a good quantitative result, even during frequency sweep with those with this test, you need to have slender specimens, so as long as you can and as thin as you can. But obviously, the small thermal chamber can be problematic from time to time. Okay, so now that we know that, we're careful. And so we use long, thin samples. And we did the frequency sweeps from 10⁻² to 10 Hertz, still given temperature, small amplitude of strain. And we build the master curve for G prime and tangent delta, as we did for E prime and tangent delta. So first thing, if we look at the shift factor for both tests, we can see, so for this building the master curve at the same reference temperature, we have equivalent shift factors. So both tests give us the same shift factors. If we want to compare G prime and G double prime for both tests, we can use Ashin correspondence principle, which basically says that all the relationships that exist in elasticity still apply in linear viscoelasticity if you replace the elastic values by their complex values, which are defined as, so for example, G star is going to be G prime plus I G double prime. Okay. So doing that, we can use the value of E star that we measured. We need to make an assumption for the bulk modulus because there are very few apparatus that give you access to the viscoelasticity of the bulk modulus. And we thought, okay, we're going to assume it as elastic because, okay, it changes over temperature, so it's viscoelastic, but the order of magnitude is 2, 3, well, when Young modulus or shear modulus are changing from 3 orders of magnitude. So we're going to assume it constant and calculate G prime and G double prime with a measured value obtained in uniaxial tension and compare it to the G prime and G double prime measured during torsion test. When we do that, we can see that we have very nice superposition. So what does it mean? That means that those tests are completely equivalent. You can characterize the linear viscoelasticity in uniaxial tension or in torsion or shearing. And if you wanted to have access, for example, to the Poisson ratio or bulk modulus to viscoelasticity by running both experiments, your experiments are not sensitive enough to do that. So you won't have access to the viscoelasticity incompressibility. Okay, so now that we know how to characterize well the linear viscoelasticity of our material, we can fit it by a simple model, generalized Maxwell model that works really well for polymer in general. And here it's fit for with 20 relaxation times. So this model is basically Maxwell elements in parallel with in parallel a spring for the long-term elasticity because we have a network here, so our polymer doesn't flow. And the relaxation function, relaxation shear modulus is defined like that, with, so GE is your elasticity at long term, and GI and TOI, number of couple, depending on the number of branch, of Maxwell branch you want to take into account. Usually for polymers, amorphous networks, it's about 20 is fine, but if you have copolymers, sometimes you need like 40. It can be much more. It's not a problem since you have a sum. It's not really costly. So basically, with we had access to, we measured G prime and G double prime in as function of the angular frequency, and so we are able to calculate GI and TOI. But it's an ill-posed problem, but there are in the literature a way to solve that correctly, and as you just seen. And so once you have this function, you can calculate the stress response of your material for any loading history at the given temperature, your reference temperature where you build your master curve. And then with the shift factor, you have access to the linear viscoelastic behavior at any temperature. It's just an extension or shrinking of the time. So basically going at low temperature glassy state, time expand, and at higher temperature in the rubbery state, time shrinks. Okay. So now, since we want to deal with shape memory property, that it's not only small infinitesimal strain, sometimes we have large transformation or large deformation. We wondered, okay, all those shift factors that are very useful for us because they make the link between the temperature and time, do they apply for finite strain? If it does apply, what we should get is being able to define the reduced time for any temperature, make the link between the reduced time at a given temperature T0, and the time at any temperature. So basically, if you apply a stress strain at a given strain rate epsilon dot at temperature T, you should have the same response than the material at temperature T0 having solicited at the strain rate depending on T0. So to try that, we set 3 tests, 3 uniaxial tension tests at large strain, temperature 45 degrees, and different strain rate. And we measured the response and tried to find other couple temperature and strain rate that shows the same stress strain response. So superimposition between the stress strain response. Okay, so at 45 degrees, we have 3 response. Basically here it's close to a rubbery state, and we are applying higher strain rate to get response that are more of viscoelastic regime stress strain response. And for each response, starting with this one, we change the temperature and look for strain rate that gave the same stress response. And we found, as you see, we were able to find for temperature within a 10-degree range, different strain rate. So we could have the same stress strain response. That means that at least in the rubbery state, we were able to find shift factor to have time temperature superposition. And it's true, it was true for the second stress strain response and the third one. So now that we observe time temperature superposition at finite strain, we compared the shift factor measured with the linear with DMA test, and the shift factor measure at finite strength with the stress strain response in uniaxial tension. And as you can see, they are completely equivalent. The limit of what you just saw is that we were not able to prove that for when the material was in glassy state. The material was or in the rubbery state or within the viscoelastic transition. The problem with rubbery state, with glassy state, is that we would have needed to be able to run some tests at high strain rate with a good accuracy, which we weren't. Okay. So what's nice now is that I can define simply constitutive equation at finite strain. So visco-hyperelastic behavior. We have measured in linear viscoelasticity the time temperature, the shift factor for the time temperature superposition, and we have measured the viscoelasticity in terms of the relaxation time and the modulus that are associated to that. And we can transpose that directly to large deformation using or a CIMO model or a thermodynamic model, such as proposed by Riz and Govinci. So I don't go through all these equations, but it's basically writing the generalized Maxwell model in finite strain. Okay, and we're going to apply that to shape memory property of our amorphous network. So here you see a ring of amorphous network that we made of acrylate. Oops, I'm going to start from the beginning. And so the property, the shape memory property for amorphous network is very simple. You go at high temperature, you're in the rubbery state. In the rubbery state, you can apply large deformations that are reversible. So by maintaining the shape and cooling down the material, then the material in the glassy state, the chain mobility is very low, and so the material will keep its shape as long as we don't expose it to high temperature. If we put it to high temperature, it's going to recover the initial shape. Okay, I have to go back to my presentation. Up. So that's the principle. Basically, you need to have elasticity at high temperature. So being able to apply large deformations that are recoverable. You apply at high temperature the temporary shape. Cool it down while maintaining the shape. When you release the stress, the shape remains, and then just by heating, you'll recover your initial shape. When we started working on that, in the literature, there were basically two types of tests, or uniaxial tension tests, which are nice for one reason, is that you can apply large deformation, but also because you can look at the shape recovery. So looking at, while you're raising the temperature, how it recovers the strain. But also what you can do is look at this, what we call abusively stress recovery, is basically you maintain the applied strain and raise the temperature and look at how the stress evolves with the temperature. And there was change of shape, but that just look at, do we have a complete recovery or not? So no quantitative following of the shape recovery. That doesn't help you look at the kinetic of the recovery and how you can predict that. So we decided to build a device, a torsion device, that would help us look at change of shape with large transformation, rather small deformation, but large transformation. And quantitatively, while we raise the temperature, look at the recovery in terms of temperature. So the idea was to have a slender rectangular sample, rise the temperature, apply a 360-degree torsion, cool it down, and then look at its recovery while we heating the sample. For that, we had a setup with a thermal chamber, a camera in front. You see the deformed sample, a mirror reflection, and we painted 2 dots, allowing us to look at while we were measuring the temperature change over time, looking at the recovery of the sample in terms of angle of recovery with the temperature. Okay, so that so the torsion, so we heated the sample above the glass transition, apply a 360-degree torsion at high temperature, cool it down, look at the shape fixity, meaning at how much the material recovered after we release the stress at low temperature, and it was excellent because basically applying 360 degrees, we ended up with 359 degrees of rotation. And then we record the torsion angle, recovery, and the temperature history while heating the sample. So that gave us not only good recovery or bad recovery, the kinetic of the recovery. And here you see the recovery according to the ramp of the ramp of temperature heating from 1.1 to 5 to 6 degrees per minute. And you can see how the recovery, it's complete, but also you can see at the kinetic and the impact of the temperature rate. We also applied a heating ramp of 1.1 degree per minute until reaching 42 degrees and try to keep it at 42 degrees and look at the recovery over time. Okay, so to model this test, we did, as I said before, we characterize the linear viscoelasticity and time temperature superposition of our material. So applying DMA frequency sweep at different temperature, build the master curve, okay, give the get the shift factor. So the shift factor, we fit them by a WLF function. I'm not a fan of it, but it's convenient, and it was in the finite element simulation code that we use. So, but if you apply, since it's really a phenomenological law. If you apply a linear approximation between the value you have, you get something that is maybe more realistic. With the viscoelastic measure, we fit a generalized Maxwell model on G prime, validate it on tangent delta, and so look at the viscoelastic spectrum. So the GI as a function of the relaxation time. And we needed additional data because we do 3D simulation. So we needed a bulk modulus, and we gave a value that was reasonable to get something that was okay in the glassy state and in the rubbery state. And also, so in torsion, we don't need it that much, but later in uniaxial tension, we'll need a linear thermal expansion coefficient. And we had two approaches. First, we did a glassy state, and we did a measure in glassy state and in the rubbery state. But then if we had to do the whole history and have good stress in uniaxial tension, we needed to measure it and give the whole history as a function of the temperature rate, because you know the linear expansion is also depending on the temperature rate. Okay, so the modeling was finite element code was done on the finite element code Abacus using Energium option for large deformation. The generalized Maxwell model and the WLF equations are available in the code for finite strain. The reference elastic behavior, so the hyperelastic behavior at a high temperature, was chosen as New-Kean with elastic modulus of 1.6, so that we measured experimentally. And what's important is that we are simulating the 5 steps of the experimental procedure: heating, deformation, cooling down, stress release. And for the last step, we really recorded experimentally the temperature history, and we prescribed this history on all the nodes. Okay, so that gives something like that. Look at our sample. We have, according to the temperature, how the material recover. And if we compare the model and the experiments, you can see that we can predict the kinetic of the shape recovery. So basically, what we just prove is something that probably a lot of people from the physics of polymer would say it's obvious, is that the shape memory property of amorphous polymer network is basic. It's a signature of intrinsic properties of this material, which are the viscoelasticity and the time temperature superposition, and that's nothing else. It's something to understand it. It's another thing to prove it, and being able to give constitutive equations that would help predict the behavior of this material. We looked also at a large strain uniaxial tension test, because it gave us a little bit more versatility. So we could look at the large strain 20 and 50%. We could look at the temperature at which we applied the strain. So 65 basically for us was the rubbery state. 45 was the beginning of the onset of the viscoelasticity. We look at the impact of the heating ramp, but more interestingly, applying uniaxial tension tests provide us with the option to look at force recovery, which in terms of constitutive modeling is a bit more challenging. If we maintain the deformation and rising the temperature, can we model how the force evolves? So with the same model, you can see that we have a very good prediction of the shape recovery. Whatever whatever the temperature rate, whatever the strain, the applied maximum strain. And also we were able to show that we also get very good stress recovery. So the constitutive equations are robust enough to also not only look at how the shape recover, but also how the force evolves with temperature. Okay, so after that, we thought about what else could we do exhibiting the linear viscoelasticity properties and the time temperature superposition in amorphous network. And we had a master's student, and that came see us master first year, and we decided to go for a fun project, which was let's make some rubber like polymer balls. And here you can see it's beads and that are usually used to make necklace. And we uh, solidify our polymer within the bead. And so once we break the glass, we get nice polymer balls. And we look at the bonds, the rebound of these balls according to the temperature. Okay. So here is the experiment that the student ran at different temperature. We're going to look at the rebound of the polymer ball. So the curing of our balls in the, we had a pump to drop the ball straight on a granite slab, and we put a piezo resistive capture to record the duration of impact on the slab. Okay, looking at also the force of contact. So at room temperature, basically the material is in glassy state, and you're gonna see he coat the ball here, so it's a really good rebound. At 88 degrees, we are within the transition, and the rebound is almost no rebound. It's very small. And at, I don't remember the temperature, but the high temperature in the rubbery state, we had very good rebound. So we look at the coefficient of restitution, which is basically the height of the rebound, defined by the height of the rebound. And if you have an elastic material, you should get 1. Well, we know in polymers there's no elasticity, but unfortunately, we didn't verify with a metal bead that this is not due to the experimental setup, and we would really get 1 for an elastic material. But what's interesting is that you can see how with the temperature, the rebound is dramatically dropping. And that has an application, actually. If you think about squash players that are warming up their ball before playing, it means basically they're around here or they're in there, and by warming up their balls, they're going to go closer to the rubbery state and have a better bounce. And so here I'm looking at the impact duration according to the temperature. And so once again, we characterize by linear viscoelasticity. Well, actually, this one is the same material, the same acrylate. So we have the linear viscoelastic behavior, the time temperature superposition. So the same constitutive equation, and we run dynamic explicit calculation, finite element with abacus again, and look at the bonds. And so you see in black here the simulation. Since we are representing the material as a generalized maximum model, it is actually, the model is really elastic in the glassy state and in the rubbery state. So that's normal that we get 1. The discrepancy here may also come from the fact that we don't have the relaxation time that comes from a dynamic impact. But if you look also at the time, the duration of impact versus temperature, we have quite satisfactory comparison. And so we were able to say, okay, knowing the linear viscoelasticity, knowing the time temperature superposition of our polymer, we are capable of predicting the rebound of our balls. Okay, and I'm gonna have a last slide for to thank my co-authors. So we worked a lot with Pierre Gilormini on the modeling and all this viscoelastic problem. Ingrid Rousseau, who's an engineer at General Motors, who was interested in shape memory polymers. We worked on the shape memory polymers with her. And the students, we had 2 master students, a PhD student who was financed by the ANR grant that I got, I think in 2010 or something like that, and financial support, so from the ANR, but also from General Motors. Thanks a lot for your attention, and I'm open to questions.
Thank you, Julie. It was a very interesting talk on linear viscoelasticity. I learned a lot personally. And so as a chair, I will take the questions from the audience, or I will ask. I have a few ones actually. Yeah. I could, so on some of your slides, I could see the new factor. I don't think you have a comment on how to get this, I think the Poisson modulus that tells, how do you estimate or measure or calculate this new factor for the 2 states of your polymer?
Okay, so that's very basic. You just do a uniaxial tension, for example, in the glassy state at cold temperature. You get by a uniaxial tension test and looking at the ratio of the transverse strain over the longitudinal strain, you get the Poisson ratio. What's very difficult, so, and in the rubbery state, we looked at on the two face of our sample. So we look at the two free face of our sample and look at the change of volume upon uniaxial tension. And you can see that it's very close to 0. So the Poisson ratio is very close to 0.5.
Okay, so the rubbers are incompressible, is it?
They're quite incompressible. They're never incompressible because, like, it's far from incompressible because the bulk modulus is more close to 3,000, which is not gigantic, right? But if you look at the change of volume when you do a uniaxial tension, it's close to 0. So that's why we say it's incompressible. But it's, from a mechanical point of view, a bulk modulus of 3,000, it's far from being incompressible, right? But so the difficult part of the Poisson ratio, and I think, and also, which is the same for the bulk modulus, the difficult part is to measure the viscoelasticity of this material, of these parameters, and it's very difficult. And we know there are very few apparatus that are doing it for the bulk modulus. And our PhD students spent 4 months in Texas Tech University. We were invited by Cindy Simon to do some measurement, and he spent 4 months there, and it didn't work out for us. We were unlucky that time; it didn't work out. But what we showed is basically in what we do. So change of shape, basically you don't have change of compressibility, and the change of uniaxial tension, well, neglect the viscoelasticity of the bulk modulus is not really a problem.
Okay, no, we have questions from YouTube that Etienne gave me. So I'm afraid there will be a question about chemistry, but maybe, okay, they look to be simple. Indra Parmar is asking, okay, what monomers and photoinitiator you were using to prepare the
so that I'm capable of it.
You can show the slide again.
Okay, so basically, we are using for photoinitiator, it's a DMPA. So the name is so complex that I don't know the whole name, but it's DMPA. And basically, I discussing with some chemists, they were telling me that it's bad. It's an old thing but for what we do, it works fine. I mean, it's a dimethyl phenol or something.
Okay, so
But
it's
in our paper on
benzophenone type. But the
so for the
corollary,
monomer,
yeah, the question is also are you sure that you go until 100% curing in your case? Have you? I mean.
okay, so that's a good question, and I asked that to a chemist actually, and especially for my beads, I was worried about my beads, and 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 I said, how do I know that it's good, my? And basically, she told me, if it's solid, you're fine. The thing is that would I have problem of post curing? I don't think so, because what we do is that we reproduce always the same mechanical behavior. So we never had problem of we didn't cross-link long enough. So from one batch to another one, we don't have the same mechanical behavior. And once we've done it, so we cure for a long time, like maybe too long, like 45 minutes. And then every time we store our samples in a freezer to avoid aging, I don't know, light aging, and it works pretty well. Like, over a period of a thesis, we don't have any problem reproducing several times the same material.
Okay, and as a continuation on this chemical part, we have Fiona from YouTube also asking, did you look at, yeah, and Jean-François will ask you a question, but maybe I just, okay, Jeff, go ahead, Jeff, you can.
Okay, I wish. Okay, just a question at the end of your talk. Maybe I'm sure I have misunderstood something regarding the efficiency of the rebound of the ball.
Mm-hmm.
So you efficiency versus temperature. Okay, it goes through a minimum around the TG. I have missed something, but how do you control the temperature of the experiment?
Oh, for that, for the rebound is, as you've seen, it's super fast, right? Like
Yeah.
So what we do is that we just warm our balls in a thermal chamber. We put it like until the temperature of the balls are equilibrated, and then we run the test once for each ball. Like, we have several balls, once for each ball. So we say, okay, during the 20 seconds or 10 seconds temperature.
It's okay. Okay, it was a previous. Okay. Okay, thank you.
And did you study the inverse system to make a hydrogel surface that would absorb totally the rebound of another ball?
Like a metal ball, like
yes,
yeah. Oh, well, so recently we tried that, and because we had with Arkema we had a study on foams, so we were interested in that. The problem is that you have to have a surface that is to have something that is reproducible, and you need to have a surface that is really flat, and it wasn't our case, so we gave up a little bit on this. But I know there's a big literature on that, and I don't see why if you characterize well the viscoelastic properties of your material, you wouldn't be able to
predict. Okay.
To predict the rebound.
Okay. Now I go back to the question by Fiona. She was asking if you tried different cross-link ratios, because you show us 10%, but is it a parameter you varied in your simulation?
10% is actually quite a lot. It's a tight network. So we tried different things, and even with like in molar mass, I think it depends on your cross-linker, I guess, but even like something like we have some, for example, we did recently some IPN. We were interested in the viscoelasticity of IPN, and so we had 2% molar mass
So IPN is interpenetrated network. Is that true?
Yeah, yeah.
So two types of polymers.
With two acrylates, and so we had to do like a loose network, right? And so we had like 2% molar mass. Works fine too. So we varied 10%. I think was about. I also use only the crosslinker sometimes, like 100% of the crosslinker. You have the length of the chains is the length of your crosslinker. You can do, and what's nice with the acrylate for us is that we were able to tailor the glass transition temperature, and so according to our need in terms of behavior and experimental setting, it's interesting that with something very simple we can change a glass transition easily.
Okay. Yeah, go ahead, Etienne.
Yeah, that's what we did. For example, when we applied here, basically, yeah, here we had so we started from a temperature that was probably room temperature 25. We raised until 42 degrees. Here the temperature was going from you see 35 to 70. Here we stop at 42, so we stopped here, and we look at over time how the temperature. So it stopped approximately here, and then we look at the recovery over time. So we have a constant at the if you have like I guess the thing is that if you applied right away a high temperature, you just need to take into account the diffusivity of temperature in your material. We haven't done that. I've done it, but but having this, I could apply, for example, on my finite element. If you see, yeah, here I applied the same temperature on all the nodes in the. If now I just apply it on the surface and have a conductivity coefficient for how the temperature change over time, I would be able to do that. There's no problem for that.
I have another one. Your model is quite general, I think, for amorphous elastomers, because it's based on the Maxwell linear response theory. But can you imagine to make a model in more complicated case if the elastomer exhibit also some semi-crystallinity? Like, I think there are some shape memory elastomers based on polyurethanes or maybe polyesters, which have also some melting temperature. And so you have the TG and the melting temperature. Do you think it will be possible to make such a model also for those more complicated cases?
So I think there's two things that are different. Yeah, you're right. Our model is really based on the glass transition temperature. And so if you look at TPE that you're using for shape memory property, usually it's not, if you have time temperature superposition, I think it should work. no problem. When you look at now crystalline material and look at the fusion and the property, it's another physics. And so, I mean, probably you need another model, other constitutive equation. First, because the physics is completely off, right?
Because maybe I'm wrong, but in this case, you can fix a shape that is not exactly, that can be different from the shape that was made when the chemical bonds were made at the cross-linking. Because here the shape that is memorized is the shape of the synthesis, right? The one given by the container.
Mm-hmm.
But with those other type of shape memory polymers, you can fix other shapes that are more maybe more complicated.
You mean you can have
for example, you can you imagine a polymer that will fix the torsion shape instead of memorizing the rectangular shape? Can you imagine of how?
Well, it's always the thing is always you could think about it's so for this material it's always the initial shape.
Yes.
The one that you're going to recover. So it depends on the initial shape you give to your material, right? So you could do whatever you want with them, especially now with 3D printing. Like, but what's true is that to apply another temporary shape, you need to apply stress. And the permanent shape, due to the cross-linking, as you said, is permanent. Like there's no way you can have another one. But that's different from the fact that if you try to predict how a recover from a temporary shape to a permanent shape, how it's going to behave, that's different from what kind of shape can you give temporary or permanent shape. And the fact that for a crystalline phase, it's fusion and crystallizing phase that is the physics of the shape recovery. You have to probably it's probably our model is probably not the best since here we're really looking at time temperature superposition and linear viscoelasticity. I think it applies well for the materials that satisfy to these properties, plus even if it's TPE, because a lot of shape memory application for TPE are dealing with the glass transition temperature.
We have another, I would say, chemistry-oriented questions. How monofunctional acrylates impart useful property because they tend to terminate polymerization and weaken network. And maybe Etienne, you can help to explain this question if you understand it. No? I don't know if Etienne is around. Okay. Okay, the kinetics is different, yes. Yeah. Yeah. Yes.
That I think the cross-linking has no impact. It has an impact on the viscoelasticity, on the mechanical properties. So of course you're going to have an impact on the shape memory property, but it's not like the shape memory property. It's no different than the viscoelastic property. It's really like you shouldn't look at it as a special property. It's really just a way to it's really due to the viscoelasticity and the time temperature superposition. And part of what I showed is were also made on an epoxy network. So it's, for us, the chemistry had, I mean, little, it wasn't important, right? We just needed a network, an amorphous network. Once we have an amorphous network, we are capable to characterize the mechanical properties and then predict the shape memory property, because that's not a special property of this material. It's just a linear viscoelasticity, well, the viscoelasticity and the time temperature superposition. Exactly.
They should, if properly measured. Maybe a last comment. It was very interesting, the discussion you made about the shape of the samples that need to be as long as possible to, I mean, there were some experimental reasons for that, as you say, the distribution of stress and everything, but is it, on a more philosophical point of view, is it something that you would make the difference between polymer mechanics and polymer physics? Is it that in mechanics you need to really take into account the shape of the sample, to not only the parameters? Or
no, it's more like you need to look at how the stress and strain are distributed in the sample. And if you use, for, so basically it's that the Saint-Venant approximation, it's really using some assumption on how the stress or the strain are distributed within the sample. And if it's not true, like you can apply Saint-Venant, it won't give you the right behavior, right? The thing is that it's something that is running a thing you need to be careful with. And for example, also something I didn't say is that the DMHU 800 doesn't give you access to the signal, so the stress or strength signal, the sinusoidal signal. So you never know when you're in the linear viscoelasticity or not. But anyway, it will give you always a value of E prime and E double prime. And sometimes those values, they don't look that off. And you need to be really careful when you don't have the signals, because actually you don't really know if you're in linear viscoelasticity or not. So that's the first point. And for the torsion, from a mechanical point of view, if you what we in the paper, like we actually, how did I notice that is that, so I had different sample, and I did some simulation, and I with the same properties and the different length of sample, and I wasn't getting the same G prime and G double prime, so I couldn't understand because it's just simulation. And so that's where we notice that we need to be careful of the fact that the grips are, the fact that the tight grips are giving non-homogeneous state of stress in the samples. But what we did is giving some kind of a rule to correct the mistake you make based on the property of the material. So if you have to run torsion tests on small samples, we gave like kind of a rule based on simulations on how to correct to have the actual property of the material.
okay, thank you. So if there are no more questions from the audience, either on Zoom or is there, okay. So I think it's a good time to close the session, and thank again Julie for this wonderful tutorial on polymer mechanics.
Thanks a lot for inviting me. That was a pleasure.
And good luck for the end of the confinement to everyone.
Okay, bye everybody.
And bye-bye. Bye-bye to everyone.
Bye.
Salut Jeff. Bon, merci. Et à bientôt pour le prochain. Ciao.